So last time we have learned about the several optimizers or the more advanced optimizer compared to the SGD. Okay, so the SGD with momentum that can climb up the small hills. Okay, by having this time of some previous term. So I mean, even in the case where their gradient suddenly becomes zero, before having this momentum, the optimization stops there. But thanks to this small term that is retaining the previous gradient, we can climb up the small hills. Okay, that is the idea of momentum, and which is very similar to real. I mean, that is happening in the real physics. Okay, momentum, their concept is actually similar to the momentum in the physics. And also we have learned about this Nesterov gradient descent. And the idea is the having calculating this gradient is happened before adding the momentum. But the idea here is we are wanting to secure this gradient by differentiating that respect to the updated parameters with the momentum. Okay, so because there's a small mismatch between this variable and the, I mean, the parameters before update. So the gradient, their direction was not very accurate before, but by modifying this, the gradient, their directions are becoming more accurate. And also we have learned about the importance of the learning rate. If it is too high or too low, the optimization, the training of the neural network, they are not good. So we have to have the proper learning rate. So if you try to learn the training code, if seeing the loss function during the epoch one, and if that loss function is diverging, then it means the learning rate is too high. So the thing you have to do is you have to reduce the epsilon value, okay? Maybe by multiplying 1 over 10, okay? So try reducing the epsilon value and confirm that the loss is gradually reducing, and rerun the experiment and confirm that the loss is gradually reducing. And if the learning rate is too low, I mean the learning might take a lot of epochs. So to secure the practicality of the learning time, I mean we have to set their scales properly. Okay. So we first try to use the bigger epsilon value and gradually reduce that to see the loss values. Okay, that is the tip for setting this learning rate. Okay, I mean this is very, I mean heuristics. This is the heuristic way to decide the learning rate. There's actually not much, principled way to decide this learning rate. Just see the loss function, and via the manual manner, we have to tune this learning rate. But there's some way to to schedule this learning rate. I mean, for the subsequent epochs, because normally the parameters are becoming saturated, and they no more require further training. So normally we at the initial epochs we need more learning rate compared to the later epochs. So normally we are using this type of very simple scheduler for the learning rate. Using this exponential function or step function to gradually reduce the learning rate. I mean, that works actually, but in optimizer side, this other graph that is having actually incorporating some consideration about the learning rate. So they can adaptively update the gradient considering the learning rate. So for the parameters which haven't changed a lot, we may have to update them in the later epochs. Okay, so for those parameters which haven't been changed a lot, we will secure the large learning rate. And for the parameters that have been changed a lot during the earlier epochs, we will secure the small learning rate. That's the idea of ADA-grad. So we somehow accumulate the gradient information during the earlier epochs in this R variable, and we divide them by the initial learning rate. Okay, that's the idea of the ADA-grad. Are you guys following this? Okay. But I mean, this becomes saturated, becomes to very large scale value quickly. So because of that, after few epochs, this ADA-grad, they lose the control over the most of the parameters, and that may be problem. So I mean, the main concern is this variable becomes uh, large quite soon. So we want to control that using this type of weight summing. Okay. And this can control the better control the scale of the R variable. So not controlling this variable not very large in earlier epochs. And in practice, RMS Pro it works better than the ADA-grad, but their conceptual motivation is very similar. Okay. And Adam is, jointly tackling both learning rate issue and also the momentum, their motivation. So Adam is optimizer upon the stochastic gradient descent. This Adam combines the learning rate consideration and also the momentum consideration. Okay. So there are actually two terms in their learning rate part. So I mean this part they are considering the concept of momentum, and for the bottom part they are considering the things for the learning rate part. So the Adam is conceptually the complete form that jointly considers both learning rate and also the momentum. But I mean, in practice, for some neural network, it can be, the SGD can be better compared to the Adam. Okay, that can happen. I mean, conceptually, even though conceptually Adam is better, but in practice, there could be some network, that is well trained via the SGD. I mean, not using Adam. Okay, that can happen. Okay, but in normal situation, because Adam is more complete form of for the optimizer. So Adam is normally works better than other works. And also in PyTorch, you can use one line of code, just changing this word to Adam or other types of optimizer to change it the optimizer. So PyTorch already implemented the optimizer. So you can only use that. Okay. And by setting these hyperparameters, you can just use that. Okay. So, during the training, seeing the initial epoch, their loss functions, you can adjust which optimizer you can use. Okay. So Adam is generally the best solution, but it depends on the neural network, their types. Okay. And also depending on their loss functions and their applications. So you have to decide by yourself. Okay, so this was the thing we have learned last time, and uh, and this is the other topic, the other important topic, which might be important for the training stage. So, the most of the thing during the training is almost fixed. So, we can vary the network, their designs, right? We can have different different dimensional filter corners or a different number of layers. We can adjust that. So, that is for changing the neural network, their structure itself. We can manage that. But besides that, the thing we can do during the training is we can change the loss function, okay? Other than the MSE loss, or even with this MSE loss, we can additionally use maybe other loss functions that can be helpful in our application. And other than that, we can also manage to use the other optimizer. Other than the SGD, we can try ADAM or RMS probe or others, okay? And other than that, the thing we can do is because this code is already fixed for the training, the thing we can do, remaining thing is, I mean, how to load these XY pairs. We can care about that, okay? Are you guys agree with this? Okay. So, I mean, actually, here in this code, there's missing how we can load these X and Y pairs. But I mean, in the previous lectures, I also explained that this X and Y can be easily loaded using the data loader implemented in the Python. But anyways, I mean, even with the data loader, the amount of pairs, okay, and how many data pairs we will use, that is remained to us, okay? So, I mean, the remaining thing is how many data, and also how, I mean, this annotation have good quality is remained problem to us, okay? So, I mean, and also when training the deep learning, which have large scale parameters, normally people say we need many training data. Okay, sorry, uh, we have we have to use many training data to prevent the overfitting phenomenon. Okay, so sorry. Because deep learning have many parameters, we have to secure many X and Y pairs and have to train the deep learning. Unless this pair is enough, the network, their parameters might be overfitted to the training data, so will not work well for the testing data. So imagine that making your network overfit to all the data, I mean, all the data you can see on Earth. I mean, this is the ideal thing, right? So, I mean, I mean, all data means both the test data and train data. I mean, I mean, let's say the images are n by n, then also each pixel have ranges from 0 to 255, okay? And also they are having RGB channels, okay? So, I mean, if we have all combination for these pixels for constituting the images, okay, and have their how to say, let's constitute this data and their annotations, okay, and if you can supply this amount of image data to the deep learning during the training, okay, especially for these permutations that have the semantic meaning, if we can show all the image data that is possible in this dimensional input. Okay, I don't know why. I mean, we can provide all the I mean combinations of the pixel values that this dimensional 2D array can have, and their Y label to the network during the training. Then I mean, it may cover up all the possibility for testing and training images. Okay, and if we can overfit our network using this amount of data during the training, then our network will for sure work well for all types of the testing data. Okay, are you guys understanding this? Okay, but in reality, there are too much. Number of data. If we combine, if we, to have all the configurations, the amount of data will be too much. Okay, even the storage, we cannot afford that. Okay, so we cannot do that actually. So normally, we the researchers are saying that we have to secure million scale data to properly train the network. Okay, especially for the deep learned neural networks, we have to secure million scale data. Okay, this is the application. So in this assignment too, which is announced yesterday, you have to do some work for the facial data. Okay, and also this is also introduced in introduction session. So for the hand pose estimation, if we can show our network all the configuration of the hand poses, then that may work well for the testing data, but in reality, it is not easy. Okay. So, if we can do this, we can achieve this type of thing. Uh, showing all the configuration, their image possibility to the network during the training, which can be possible on Earth. Okay, then that training might be good, but we cannot do that. Okay, so the thing we can do instead is secure, anyways, large scale data or million scale data, and then also consider their distribution. That is the thing we can do, maybe, right? So, even though we secure many data in the large scale or million scale, there are, let's say they are having very similar samples in their data, then the training might be not very good. Are you guys understanding this? Okay. It is natural thing, right? So, first, we want to secure the quantity of the samples, but we also have to consider their distribution. Okay, are you guys understanding this? Okay. So I want to introduce two widely used method that is, I mean, uh, developed for visualizing the data samples. Okay, two popular data visualization techniques I want to introduce to you. So, for example, in MNIST data, which is simplest image classification data, it has 28 by 28 by grayscale image, right? And normally we use those pixel values as the feature, okay, by flattening those two-dimensional array into one-dimensional feature vector. So we use their pixel values by flattening them. We use that as 784-dimensional one-dimensional vector, and we use that as the feature to map them to the class, okay, semantic classes from 0 to 8. Okay, that is the handwritten classification data. But visualizing this deep dimensional data in some 784 dimensional space is, not trivial, right? Not easy. Okay. So normally what we do is because we are living in the 3D space, right? Normally we reduce the dimension of this feature to 2 dimension or 3 dimension, okay? And having this type of 2 dimensional graph or even having one more axis, we can, reduce that to 3 dimensional space and wanting to visualize that in that reduced space. Okay. that is the technique I want to introduce here. And the first technique is called as PCA, the Principal Component Analysis. Okay, that is the first method, and the other is TISNI. We will learn about this. So here, for the MNIST, we are reducing the low 784 dimensional feature into two-dimensional vector for each sample. And then we use one dimension as the x-axis and project the other dimensional feature into y-axis. And then we can now visualize this type of figure. Are you guys understanding this? Okay. And this is the result. I mean, so the PCA and TISNI, they are the technique that can reduce the dimension of the features. Okay. Using PCA, we can reduce this dimensional feature to two dimension or to other arbitrary dimensional signal. We can reduce them. Okay. And also using the TISNI, we can also do the similar thing. Okay. But their specific methods are slightly different. Okay. That's what PCA and TISNI does. Okay. So indeed, here the different colors, they are indicating the samples from different classes in MNIST. Okay, so here there are some color list here, right? So anyways, PCA can map those features into this space. Okay, but you can see somehow they are I mean the color having the similar color, they are mapped to the similar XY space, okay, because of their feature similarity. And also here you can see also the features with same color, they are I mean clustered together, okay, because there's feature similarity. And indeed, by seeing this figure, you can feel like that this feature is having some discriminative power. Okay, so even with some Euclidean measure, okay, even using Euclidean distance, you can now how to say, uh, I mean, discriminate this and these samples, their semantic classes. Okay, right? But I mean, for some other features, I mean, if you draw the figures like this, then they somehow they could be uh, mixed together, and you can feel like that this feature is not that suitable for discriminating different classes. Okay, so you can feel like that. Okay, and also you can feel those training data whether they can cover I mean, how to say? I mean, sometimes also, how to say? Some training data they are only having this coverage, even though I mean, their variance could be very small. Okay, seeing this visualization, anyways, you can feel like that the data itself having good distribution or not. Okay. So visualizing their techniques are useful for, uh, I mean, securing good quality data. Okay, even though we cannot secure all the data in the world, but we want to secure a proper amount of data, but wanting to secure their quality. Okay, by visualizing them. And this is the code for this visualization. Okay. So, I mean, this is for importing some packages. So, I mean, this is the package for PCA and TISNI. So you can use scikit-learn. Maybe you learned about this in AIP2 or others. So this is the machine learning package. So they are already implementing this famous algorithm. And this is for visualizing the 2D graph. Okay. And this is for opening the MNIST data. Okay, this dimensional feature, they are retained here, and why they are the labels, 10 class labels, okay, indicating 0 to 9 handwritten digit, okay. Okay, and you are wanting to, somehow split the data here, okay. But for visualizing this figure, I apply PCA with true component. So this parameter is indicating that we want to reduce the dimension from this dimension to 2 dimensions. So if you specify here 3, then the resultant feature might be in the 3D space. Okay. And anyways, here is the graph visualization. So uh, df subset. So here, anyways, the for the data, uh, this is the PCA result, which is 2-dimensional feature resultant from the PCA, and this is indicating all data for their first dimensional feature, and this is all data for second dimensions, and we are mapping them to X and Y axis here, and we are visualizing them here. Okay, X is PCA1, okay, and Y axis, that is the PCA2, okay. Second dimension of the PCA axis, okay. So by doing that, you can visualize this type of figure, okay. And t-SNE, that is also similar. So you, you can apply t-SNE here, and by setting this variable, you can adjust the number of dimension, the result for the resultant vector, okay. And this is the t-SNE result, and registering their first and second axis as the X and Y in this figure, and draw this type of figure, okay. And basically, what PCA does, I will now wanting to explain here. Okay, so PCA, their name, they are saying that principal component analysis. In PCA, what they want to achieve is they want to find some new axis uh, that have highest variance. Okay, have the highest variance. Let's say this is the data distribution in their original space. Let's say in this dimensional space, the data, we cannot visualize that, we cannot see that, but in this space, the original low feature vectors will be there, right? And we want to find the axis, find the new axis that have the highest variance. I will show this figure first. Let's say if data distributed in this way, then uh, if we select some axis in this way, then those data will be mapped to this space, and they will be seen in the humans can only see that this direction, okay, for this number of data. Okay, are you guys understanding this? But if we decide the new axis in this way, let's say this is the new axis, then the features will be mapped to this axis by projecting them into this new axis. Okay, and then the humans now can better discriminate, better see the data distribution. Okay, Are you guys understanding this? So let's say this is X samples, and this is circle samples. They are let's say they are having uh, different classes. Then we can say X, their data is distributed in this part, and the circle samples are distributed in this part. And maybe this is could be some boundary. I mean, that can discriminate these two different classes. Okay, so when seeing from this axis, this could be easily seen, but when seen from this axis, all the X and circle samples, they are mixed. They are mixed, right? So when they are projected in this space, X is here, circle is here, again, X is here, right? So when seen from some axis, the feature discrimination is not that easy. Are you guys understanding this, right? So this is the idea for that. So PCA, they are wanting to call the new axis that have the largest variance as the principal component. Okay, principal component means they want to secure the axis as the principal component that have the largest variance like this. So here, when seen from this axis, the data, their distribution is having the high variance. Okay, they are spread large in that spanning that axis. Are you guys understanding this? But here, they are having very low variance. Their range, they are limited by this amount. Okay, but here their variance is very large. Okay, so I mean, for the axis that have the maximum variance, we can maybe easily discriminate the data samples. And I mean, anyways, our purpose here is to see data distribution, not for discriminating or classifying the data themselves. So for the visualization purpose, having, I mean, high variance, that is helpful, right? So the PCA, their motivation is to find the principal component, okay, that have the highest variance, okay. And next, what they want to do is, when selecting the first principal component that have the highest variance, the next is they want to, I mean, when, let's say this E1 is the first axis that have the maximum variance, okay? Then we have to decide the next axis, and that would be the second axis. This might have the next maximum variance. At the same time, it have to be orthogonal to E1. Okay. So as the basis for describing the data samples, the axes have to be, their base have to be orthogonal to each other. Okay, so we have to have we have to have this kind of constraint that constraining all of the principal components, they are orthogonal to each other. And third, when deciding the third axis, next, they may have next maximum variance, also orthogonal to both E1 and E2. Okay. So this is happened during the PCA. Okay. And also, if you select only two axes, okay, if you when seeing the data, if you secure only two axes, that is the thing that reduces low dimensional vector to two dimension. Okay, if you secure one more, then it means you are reducing row vector to a three-dimensional space. And if you secure one more, if you find one more axis and visualize the data, then you are using four axes, and it is mapping the row features into four-dimensional space. Okay, are you guys understanding this? Okay. So axis that can represent the largest variance, that is the principal component, and axes have to be orthogonal to each other. Okay, and actually, this slide is showing the method. I mean, the operation that is happening during calculating PCA. Okay, so first, uh, I mean, you have to make this type of covariance matrix. Okay. Okay. And then you can apply this type of eigenvector decomposition. Sorry. I mean, you apply this C is the covariance matrix, okay, having this type of term. Then you may have to apply this type of eigenvector decomposition, okay. So, and then find the eigenvector and eigenvalue for this covariance matrix, okay? And then, I mean, I'm not sure you are familiar with this linear algebra. We first find the eigenvalue and eigenvector for the covariance matrix, and the variance of data samples. I mean, that is the way to find the principal component. Okay, that corresponds to the scale of the eigenvalue. Okay, I mean, you at this stage, I think you can believe this method. I mean, believe this sentence. Okay, so data samples, their variance could be, explained by the eigenvalue, their size. So, I mean, what they do is they sort the eigenvector, in the descending order according to their eigenvalues. Okay. So because eigenvalues, they are encoding the variance of the data, and also eigenvector, that becomes the axis. Actually, that becomes the axis. Okay. I mean, and also eigenvector, they are orthogonal to each other. Okay, so that actually meets the constraint, that we want for this type of thing. So to obtain this type of thing, we apply, eigenvalue decomposition on the covariance matrix. And we sort the eigenvectors according to their eigenvalues. And also by nature, eigenvectors, they are orthogonal to each other. So if we select the eigenvector whose eigenvalue is the largest, then we can call that as the first axis, okay? And the second axis, we choose the second eigenvector, then that is the new axis that is having next largest variance. At the same time, E2 is orthogonal to E1 because we did eigenvalue decomposition. Okay. So this is actually how we obtain the principal components, okay, from the arbitrary feature vectors. But their concept is doing this kind of thing, okay? Wanting to find the one that have the largest variance, and axis, those have to be orthogonal to each other. But for implementing that, we first calculate the covariance matrix between the data, and then apply eigenvector decomposition. Then the eigenvalues are located in this part, okay? And by sorting eigen, how to say, vectors according to their scales, uh, we can somehow select the first principal component and second principal component and so on. Okay? That's the PCA. Uh, I mean, uh, this is the visualization that I explained in this part. Okay, so getting good access that is in general important. Okay, to visualize the data. Okay, and the other way to reduce the dimension, for example, from this dimension to two dimension, which is frequently used technique is t-SNE. Okay, and what they do is, I mean, they how to say, focusing on the retaining feature similarity, feature their pairwise similarity. Okay, so let's say this xi is i's sample, and j, which means the pairwise sample to the i's sample. Okay, and this is somehow measuring their similarity in the feature space. Okay, this exponential, they are calculating their distance or similarity. Okay, so and this bottom part, they are adding all the distance between the data samples. Okay, this is summing over all the pairwise data, and this means, considering all other pairwise relationship between all other samples, uh, how to say, what is how much I and J samples they are similar. Somehow this Pj given I, they are encoding that information. Okay, so considering all other data pairs, how much I and J samples they are similar. Okay, that is encoded in this probability. And this Q means we are wanting to map this. This is the similarity which is obtained in the original high dimensional space. Okay, but this Q is the similar thing that is obtained in the reduced dimensional space, two-dimensional, for example, space. Okay, and what they wanting to achieve in t-SNE is they want to reduce the KL divergence between this P and Q, which is P is the original space, their feature similarity between I and J sample, and Q is the feature similarity in new reduced space. Okay, and we in KL divergence, we learned about this when learning about the cross entropy laws. So by minimizing this KL divergence between these two distribution, we can somehow making these two similar or same. Okay, by minimizing this cost, we can make this P and Q same. Okay, so somehow this t-SNE is enforcing to retain the similarity in the original high dimensional space into new space, which is reduced space. Okay, are you guys understanding this? Okay, so minimize the discrepancy between the pairwise similarity, their relative locations in original and reduced space. That's what happened in the t-SNE. And sometimes, normally this is used, which is the normal distribution, but normal distribution, this green graph is denoting the normal distribution. When their distribution is close to the mean, uh, I mean, they have the higher value, but when samples that have that is far from the normal, far from average, maybe the how to say this normal distribution cannot model their pairwise. I mean, distances where they are regarding them as all zero when far from the average, being far from the average, they encode them same as zero. So to prevent this problem, later Disney, they are sometimes use the T distribution when, how to say, modeling their, I mean, Q distribution. So that is, looks like this, okay? So they want to reduce this type of problem, not properly encoding the pairwise distance between samples, which is might be far from the average. Okay, so this is the Disney. Okay, so I mean, using this type of energy function, I mean this type of cost defining KL divergence between P and Q, they can make the, how to say, new locations for the samples. That is the Q. Okay, that is a Disney. So, I mean, for visualizing, I mean, this is the lesson from here. So, to visualize high dimensional data for humans to see, we have to map them to a low dimensional space, which is two-dimensional space. And there are two ways of achieving that. One is the PCA, and the other one is the Disney. Okay, their method is slightly different. Disney, they wanting to retain the pairwise similarity. PCA, they wanting to secure new axes that have the high variance. Okay, and you can implement this technique easily using the scikit-learn maybe instead of implementing them all by yourself. Okay. Uh, and the other, I mean, topic is in the many applications in the computer vision, uh, I mean, application wise, there are many large scale data sets is already available. So for example, this is the pose estimation domain that our lab is actively conducting actually. So, I mean, this is just an example. So these names, they are showing the, I mean, benchmark their name. So ICVL data, that is some benchmark having a few thousand samples. And this is also small scale data benchmark that have few thousand. This is similar, but this is big hand data that have the million scale data. So this is thousand scale, okay, few thousand scale data, which is small in scale. So the interesting is if we train using ICVL, their training split and testing on their ICVL's testing split, in benchmark, their accuracy is best, okay? But when trained on this small scale data and testing on other types of benchmark, this is the, how to say, the, I mean, the error. This is showing the error, okay, the distance between ground truth and prediction. So less is better. So when trained on the same benchmark training data and testing on the same benchmark, when the benchmark itself is small, that is, how to say, producing good result, but testing on different benchmark, their error becomes higher. I mean, this NYU MSRC, that is similar. When training on them and testing on them, then their accuracy is compared to other training data, other small scale training data. I mean, this lot is trained on small scale other benchmark and testing on NYU. And this is training on NYU and testing on NYU. Compared to other small scale training data, when trained by their original training split, their error is minimized. But anyways, when testing on other small scale benchmark, their error is becoming higher. Okay, that is actually the problem in small scale data. But weekend, as I mentioned, and same trend can be seen in MSRC, which is the small scale data. But weekend, which is the largest data in 3D pose estimation, and I mean, when trained on weekend, when and also evaluated on other benchmark, even though they are not trained on ICBL, their performance, their error is anyways better and even better than the one obtained by NYU trained result. Okay, and I mean this is also higher, but compared to other small scale trained models, they are becoming better. Okay, and for weekend, also they are I mean good. Okay, compared to other trained model, other small scale data trained models. Okay. So, I mean, this is the merit of having million scale or the large scale data set. Okay, so securing data, large scale data with good quality distribution, that is very important in deep learning. And also, this is not thousand scale, but anyways, this is 17,000 scale and 81,000 number of samples this NIU is having. And this is 76,000 images contained in this MSRA. And this is 2.2 million samples contained in this beacon. Okay. And if you visualize these three different beacon, ICVL, and NYU data in I mean their coverage on their viewpoint when I mean capturing the images, there is a camera viewpoint, and also because we are dealing with pose estimation, I mean the data itself have to have many poses. Okay, this articulation angle is encoding the pose. Okay, the diversity of pose. Okay, and this is combined, pose and viewpoint combined. Okay, so anyways, these blue samples here, all the blue samples, they are showing beacon samples. We are here. What they did is they are applying t algorithm to reduce the input, the data samples in different benchmark and applying t and visualizing them in the 2D space. This beacon is the sample contained in the million scale data. And you can see, anyways, the blue samples are covering ICBL or NIU data samples. So NIU, they are denoted as green samples, and ICBL, they are denoted as red samples. Okay, these are 1,000 scale data and beacon million scale data. They are covering up the 1,000 scale data, and that is actually the reason why this beacon, even with beacon trained data, they can cover up the testing samples of the other small scale data. Okay, so in distribution, you can confirm that this million scale data, they are covering up the 1,000 scale data, their coverage. Okay, and this is the simple technique. We can increase the number of data, the data augmentation we already learned about. Okay, so I will skip this part. The other way of increasing the number of data is using this type of cloud resources. This is not very important, I mean, interesting topic maybe. So, I mean, cloud, sorry, cloud, not cloud, cloud resources. Okay. I mean, if you use this Amazon Mechanical Turk, I mean, and paying some money, then some some people in is hired to do some job, and we can use that human resources to annotate this kind of data. So this MS COCO data is the data proposed by Microsoft, okay? And they are making million scale data by using this AMT, Amazon Mechanical Turk, the crowd source, okay? So given this image, they make this bounding box and also the segmentation mask, okay? And some discriminate their instances as well, okay? So they are making many data using this crowd source, okay? They are having this number of categories, okay? This was very sensational. Even till today, we are using this Microsoft COCO dataset for object detection task. Okay, they are frequently involved dataset. Okay, and the naive way to obtain this high quality data, million scale data, is to use the crowdsourcing. Labels. Okay, and this is also interesting graph. So you can see this is the precision. Y-axis means the precision of the annotation quality. And x-axis, that is showing the recall. So precision recall, we already learned about. Recall means the ability to capture cover all the ground truth. And precision, that is meaning, how to say, uh, when annotated, their quality, that is the precision. Okay, sorry. And this graph is saying that they are hiring 8 workers in AMT system to collect the annotation, and this is the number of AMT workers. They are visualizing the AMT worker. Interestingly, if you involve more worker, the precision is becoming less. Okay, I don't know why, but maybe they make some confusions and they are not expert in the data collection part. So if you involve more worker, their precision could be becoming less. But their recall is becoming better because they uh, annotate any missing, they remove any missing, annotated missing object, okay? By collaborating with this number of workers for one image, they can, cover up the ground truth. But this is the graph for, how to say, 1, 2, 3, 4, 5, 6, 7 experts involved. So their precision for the annotation is very high. Even with one expert, their precision is higher than just crowdsourced worker. Okay, but what they say is expert. They are good in precision, but seeing from the recall aspect, involving 8 workers, they are better in recall, not missing, saying that they are not missing the ground truth for an image. If we involve 8 worker, crowdsourced worker, even better than one expert. Okay, so they are. This is the reason why they involve 8 AMT worker to collect the MS COCO data set, and seeing the graph, 8 to 10, that is not increasing recall much, but reducing the precision only. So that's the other reason why they don't involve 10 AMT workers, but involve only 8 AMT worker. Okay. So, anyways, we can use this type of crowdsource to annotate our data, okay, when collecting our data. This is the specific method this MS COCO used. First, to obtain the fine segmentation map and bounding box, they first label the category in the image first. Okay, roughly in this partial location there are dog, and roughly in this partial location there are bottle. They do this first, and next round they make this type of cross, okay, in the image to roughly also denote the location of the object. And then next round, they obtain the fine segmentation map. This is what uh, I mean. I mean, uh, they involve 22 workers for obtaining this segmentation map as well. Okay, for the detection, they involve 8 workers, but for the segmentation, they involve more workers. Okay. Anyways, this is the procedure. They from coarse to fine level, they gradually obtain the finer, the annotations. Okay, this is the way to increase the amount of data, which is very important for deep learning. Another way in vision domain to easily augment the data is using this synthetic data. This is the last topic, actually. So, you may see that these persons in the image, they are not realistic person. We are not capturing this photograph by capturing some real person, but instead they are rendered from graphics model. Okay, this is actually another way of collecting the large scale, large amount of data in vision domain. Okay. So, this is another paper that does this type of things, okay, using GTA game engine. Maybe some of you are already familiar with this GTA, their game engine. Using their GTA, they are having very high quality simulation, I mean, for the modeling the city, okay, using their, game engine. They can render it to even for the segmentation map. Okay, they already in the game engine they know this part is human head and this is bicycle and this is car object, right? So using the merit of using game engine, this type of synthetic data is obtaining this annotation becomes very fast. Okay. So, this type of crowdsourced resources, we need to involve very many resources to make the annotation for, especially for the segmentation. But it takes few seconds, 1 or 2 seconds to render this image from the game engine. Okay. And we can use this as the RGB image. Okay. The input image X. Okay. And use this as the Y label. Okay. So this is the merit of the synthetic data, okay? And there are actually many, how to say, uh, graphics models for hand and human body. And also, but especially for the 3D reconstruction task, okay? And in assignment 1, you also have to estimate the pose of the facial, pose of the face, that's the 3D reconstruction. But securing the labels for the 3D tasks is very high, very difficult actually. In here, segmentation mask and object detection bounding box, this type of thing, you can easily, not easily, but if you take time, then you can secure that. But in 3D space, obtaining, even for 2D pose, it is easy. If you take time, you can secure the accurate ground truth, but it is hard to secure the depth value, their accurate value uh, in 3D reconstruction task. Okay, so especially for that, synthetic data rendering from synthetic data, even RGB can be rendered from the graphics engine. And we can also secure the depth map or segmentation map and also the pose, 3D poses, okay? We can easily obtain that using the graphics engine. But I mean, this is another, I mean, examples. So even we can render when using the human model and their hand model and object model, we can render RGBs without object. This is label is wrong. We can get RGB image without object. There's no object here, but here there's an object. So we can render the same RGB image with and without object, okay? And also we can get them in different modality, segmentation, mask, and depth, okay? This is the merit of the graphics engine. So this is an example for capturing this, I mean, rendered images, synthetic data from the 3D model. And this is the examples for that, okay? And when given this graphics engine, you can make this type of RGB image easily, okay? But I mean, there's one more issue for this. So I mean, I mean, this is the last slide maybe, okay, for today. Sorry, I mean, let's finish this, okay? So there's actually a gap between real and synthetic data. Synthetic data, that is RGB image rendered using the graphics engine, okay? I mean, even humans can feel that this is not that realistic. I mean, this is more likely to animation data, not the realistic data, okay? So the issue is we have to make some deep model, deep learning architecture that is working for real test data. So in the real world, we want to use the deep learning model. For example, here, we capture the real hand and wanting to estimate 3D poses for this real hand. We are not wanting to achieve the pose estimation for synthetic data. We don't want to do that. Okay. In practice, we always want to make our system, our 3D pose estimator or object detection algorithm working for real world photograph. Okay. So our testing data should be real world data. But I mean, as I mentioned, we can involve synthetic data in our training. Okay. But there's a gap between real and synthetic, and even humans can feel that the synthetic data is more like animation, not very realistic. So the problem here is the machine learning, deep learning model that is trained on synthetic data sometimes does not always generalize well to the real world data due to that domain gap between real and synthetic data. The machine learning model that is having many synthetic data, that is trained on synthetic data, does not working well. This means it does not working well sometimes to the real world testing data. Okay, that is showing I mean, the problem. I mean, this gap between real and synthetic. Are you guys understanding this? Okay, this is not difficult concept. So there has been some algorithm that want to, fill the gap between real and synthetic by involving some generative AI. So these days, we can even draw some figures using the generative AI like diffusion or GAN. So this is the synthetic data that is rendered from the graphics engine. And using this synthetic as input, there's some effort to refine them, reflecting some real world noises. Okay, so, and this is the same thing. This is the synthetic image that is rendered from the graphics engine that is having very unnatural eye data. But in the refined one, they are having more realistic eyes. So using the generative AI if you are interested in this, then you can refer this old paper. And later on, still the research, related research is very important for the vision domain. So anyways, generative AI can fill this gap. So there has been effort for this, okay? And this is also interesting result. This is the last one I want to tell here. So this is a real image, and this is the synthetic. And actually, this paper that is proposed by Apple and actually received the Best Paper Award in CVPR 2017. And they trained the refiner that refine the synthetic data, which is unnatural, to have the reality in the refined images, in the output images. So they used the generative AI. At that time, the GAN was the state-of-the-art generative AI. So refiner was constituted with the GAN algorithm. And anyways, they want to fill the gap between real and synthetic via this generative AI. And this is an interesting result. If their training data is composed of pure synthetic data, their accuracy is limited. But if they use refined synthetic data, their accuracy is slightly improved. And if they train their network using the real data, then compared to synthetic trained model, their performance is very good. Okay. But even using 3 times synthetic data compared to this, the amount of training data is 3 times, then it is becoming better than real data, maybe, 1 time quantity. Okay. But if we use refined synthetic data 3 times, then that is performing best. Okay, that's the result presented in this paper. So that is, indicating the gap between real and synthetic as well. So, anyways, this is the techniques that you can imagine when when wanting to increase the amount of data in vision domain. Okay. Okay, thanks. And I want to finish today's lecture here.